Good afternoon, everyone. We have already looked at the error backpropagation training algorithm, and we have solved problems on that. So next we'll look at the learning factors which influence the error backpropagation training algorithm. So given here is a list of the learning factors for the error backpropagation training algorithm, EBPTA. You have the first learning factor, that is the initial weights and the biases that you set for the network. The next one is what is the weight adjustment strategy? How are you going to update the weights? Whether we go for a cumulative weight adjustment or we go for an incremental weight adjustment. So we will look at these strategies. Next, the steepness of the activation function. So we all know that whenever we are talking about a neuron in any network, we always have or compute the output of that neuron using an activation function. So several such activation functions we have already looked at, and some standard activation functions where we have looked at, especially when I'm talking about steepness, I'm talking about the sigmoid activation function. The sigmoid activation function is having a slope. So how steep it is. So that is also one of the factors which actually affects the training of a network using eBPTA. So we will just go through that um, idea where steepness, how steepness is going to affect the training of the network. Next learning factor is the learning constant. So in your weight update equation, there is one constant which actually takes care of how slow or how fast the training progresses, and that is nothing but the learning constant. Next learning factor is the momentum method. So far, whatever algorithm we have looked at the very basic error backpropagation training algorithm, where we haven't talked about this yet. But several such variants of eBPTA you make use of an additional term while updating the weights, which is actually used to speed up the training. This actually is used for speeding up the training, and that method is called as the momentum method. There's a term which is added to the weight update equation, which actually speeds up the training. Next, and the data representation. So what is the kind of network architecture we are going to look at while designing it for a problem, for a certain problem? How do we decide the network architecture? What should come in the input? How many neurons should be in the input, the output, the hidden layer? What is the way in which we represent the data? So whatever training patterns we have, how do we represent it? And that certainly affects the learning for any problem and training the network. That is yet another learning. We have the number of hidden neurons. So how many hidden neurons are necessary when we are designing the hidden layer? When we are talking about the entire network architecture comprised in terms of the input, hidden, and output layer. The input and output has its own way. I mean, there is a separate way. So it depends what all are the features. So input can be almost readily decided by that. But in case of hidden neurons, how do we decide that magic number which is going to give us the right solution to solve the problem? Okay, is there any such magic formula that is there which will give us the answer, or what is it? What is the way to go about this? Next learning factor is the training time. Training time. So how is the training time decided? What decides the training time? How long you should train for? Do you train for hours? I mean, is there a fixed time for a given network, or is there some guideline that you need to follow? You know, that also we'll discuss. So all these actually will, in summary, will actually contribute to training your networks as successfully using the error backpropagation training algorithm. So we will look at these factors one by one in detail. So the first factor is initial weights and biases. So the weights are usually initialized to small and random values. The weights of the network are initialized to small random values. So whatever the initial weights are, that will definitely affect the final solution. The final solution will be decided by the initial weights that are chosen. So certain things that you need to keep in mind. So if all weights are equal weights, so if you start out at equal weights at the beginning, the initial weight vector is all equal weights, and the solution or the pattern space is such that you require unequal weights to be developed, then it will not be trained properly. You will not get the classification line correctly because you have started with equal weights. So there is a pull towards all directions. So it's not going to work. So sometimes what happens is, if the weights are not properly initialized, then certain examples which are present in the training set, um, the network will not be able to actually understand those patterns, classify them. Okay, so then what we need to do is we need to start with another set of random weights. So what happens is, sometimes you start training and with some set of random weights initially, and then you realize that you are going nowhere, so you need to stop and again reinitialize. Now however, this initial weights that you choose, there are certain um, weight initializers which are available, which you can directly use. So you have, if you remember the example that I had shared with you, which where we had a quiz, in that we had used uniform random weights to initialize the network. Okay, there are certain initializers, built-in initializers, which you can use, which are also provided in the libraries that you have. uh, you have Xavier initializer. Okay, there's certain uh, initializers which are present, which you can work around, use, and you can experiment with. But you need to experiment. You cannot, only thing is, you should not start with equal weights, because your solution might not require that. Many times it will fail. So that is a guideline that you need to follow. Uniform random is a good choice. Okay. Small random values from a small distribution. So there was a range between -1 to +1, or -0.5 to +0.5, the random weights. So that range also matters, not very high weights. Small random weights work well generally, that is the case. So that is the case with initial weights. If training is not progressing as you wish, you might want to reinitialize using some other weight initializer or another distribution. Okay, so that is about. Is my screen visible?
Yes, ma'am.
Hello, am I audible?
Yeah, I think the screen is on. Yeah, it is on initial weights and biases now.
I'm not able to hear you.
Hello.
Just a minute, I'll just join back, give me a minute. Yes. So that is about the initial weights. Next learning factor is the way in which we update the weights. So the usual algorithm that we have seen, what we do is we first present the pattern, then we compute the error. So a single pattern is given to the net. So from the training set, select the pattern, first pattern, take the first pattern, give it to the network, compute the error signals, and then update the weights. Okay. Then what do? You take the second pattern, give it to the network, right? Compute the error signals, update the weights. That is the usual way in which we have seen weight update for all the algorithms that we have discussed so far. Okay. Such a kind of weight update is said to be incremental weight update. It is said to be incremental weight update. So the weight update uh, is one by one, one pattern at a time. Okay, so that is called as incremental update, one pattern at a time. So for a given pattern, you find out what is the error, update the weights. Okay, single pattern error reduction, that is called. So the advantage of this situation, this kind of a scheme is that you are actually using the true gradient descent mechanism. So you are going one step at a time. The error quantity is small, right? You are not updating all at once. A large amount of error is not updated. One pattern at a time it is. So the error is also significantly smaller than you consider all the patterns. And that if you consider all the patterns, okay. So this algorithm is actually a true gradient descent which is going downhill, and the disadvantage is that the network might be skewed towards the most recent patterns in the cycle. So the last few patterns that it has seen, the network is skewed towards that. Okay. So for this purpose, what is done is a small training constant, a learning constant is used. So what you need to do is, since you're in your weight update equation, you have CRX, or right, eta times del, delta E, right? So that learning constant is also there in the weight update. So this eta times the learning constant that you have, it has to be very small. Then what will happen? What if the error, if then it will be slower, so it will not be as skewed as if you are taking it to be large. So if it is 1, it will be directly proportional to that. It will be exactly equal to that error. Okay, the weight update in that direction. So that is one way. Or cumulative weight adjustment is done. Now cumulative weight adjustment, what happens is, for all the patterns that you have, at the end of all the patterns, you are updating the weights. So delta W is equal to summation for all the patterns, the summation of all the error signals or the weight changes for all the patterns together at one go is given or added to the weights. So weights are updated by using error signals which are accumulated, and then at one go they are updated. Okay. So there are different terminologies which are used for this. So you must have come across uh, stochastic gradient descent. You must have come across batch gradient descent. You must have come across mini batch. Okay. Now stochastic is the incremental weight update that you have. Batch is Everything is all the patterns in your training set is the batch. Okay. Now, batch could be, I mean, mini batch is a variant of the batch actually. So what you do is, rather than, so if there are a large number of patterns that you have in your training set, like 10,000 patterns are there in your training set, then what you do is, rather than giving it all at the same time, I mean, doing the error update at the same time, weight update at the same time, what we do is we divide it into smaller batches of size 16, size 32, whatever. You must have seen this. Those are called mini batches. So weight update. So suppose there are some samples, large number of samples with you, you will not update the weights as a cumulative weight adjustment at the end, after the last training pattern, not all in at one go, but at intervals, regular intervals. So after, say, some 16 patterns, one batch, which is one batch, you will update the weights. Then following this, next 16 patterns is the second batch. This is batch 1, this is batch 2. So at the end of the next 16 patterns, every 16 patterns you're going to update the weights. So that is known as mini batch. Okay. So these are several variants which we look at and which are used in practice rather than incremental weight update. And incremental weight update, what happens is, in mostly in deep learning and wherever the training pattern, the number of training patterns is very large, what happens is, you need to divide it into batches, because incremental will be very slow, and batch, I mean, you don't have that much memory to bring everything into, I mean, to have a single batch. So what you need to do is you need to divide into smaller batches, mini batches. So in practice, mini batches are used for deep learning kind of scenarios. Okay, for simple MLP, very simple problems where we are just going for one or two layers of hidden, one or two hidden layers. Then in that case, what you do is, you can go for incremental weight or batch update, because the number of the data also is small. The number of training patterns is also low. So you have to choose accordingly, whatever is the problem, whatever the network that you're using, whether you want to go for cumulative weight adjustment or you want to go for incremental weight adjustment. If you're going for cumulative weight adjustment, whether you want to go for a single batch or you want to go for mini batches, that depends on the data set, that depends on the network architecture that you're using. So if you're going for this incremental weight update, that is for a smaller network, when I'm talking about a smaller network, then it is advisable to, to remove the skewness that you have. So what is the problem with the incremental weight adjustment? The last few recent patterns, the network is skewed towards that. So what you need to do is you need to introduce a certain amount of randomness into the training. So what do? You actually give the patterns in a random sequence every time. You do not give it in the same order. Like, so if you have the training patterns in some order, so there are, say, n patterns, p1, p2 up till pn in your training set. Okay, so in the first epoch or in the first training cycle, you give p1, p2 some order, some permutation. In the next training cycle, so that this is epoch 1, in the next training cycle, what you do, you just shuffle it, some other order. Pn is here somewhere, p3 is here. So you keep on shuffling the sequence of input patterns that you're giving to the network if you're going for incremental weight adjustment. So that is what is done internally. If you have not implemented it by hand, if you have not implemented MLP by hand, that is what is happening inside. A random sequence is given. Random sequence is chosen for the patterns. Okay, if you're using the library function dot fit, model dot fit, that is what is happening. Random sequence is given. Next. Next is the steepness of the activation function. Now, when we talk about the steepness of the activation function, the steepness of the activation function actually is the parameter lambda that we have in the network function, the activation function that we have, f of net, right? Lambda is called as a steepness parameter, or lambda characterizes the steepness of the function. Okay. Now, whenever we are computing delta O and delta Y, the error signals, we know that in the error signals, in case of EBPTA, we have this term, the derivative term, f dash net. So, both the choice as well as the shape of the activation function will strongly affect the speed of the learning. So, if we are considering this function, this activation function, which is this activation function? This is the bipolar sigmoid. So, if we are considering the bipolar sigmoid activation function, we can find the derivative. So, this is the derivative if we are considering lambda. Usually, what we do is we make lambda as 1, and that is the case actually that needs to be followed, which will come to. But f dash net is this. If this is activation function, this is f dash net. 2 lambda e raised to minus lambda net. 1 plus. When you solve this, find out the derivative, you'll get this. Okay. Now, if you look at this particular term, the derivative, this term, the derivative of net, f of net, you can notice that it reaches a maximum value of 0.5 lambda at net is equal to 0, right? So, 0.5 lambda at net is equal to 0. So, if you substitute net equal to 0 in this equation, substitute net equal to 0, so what will happen? You will get 2 times, if you just substitute, put net is equal to 0 here. What are you getting? 2 times lambda times e raised to 0, that is 1, right? Divided by 1 plus, again e raised to 0 is 1 square, that is 2 lambda by 4, right? That is nothing but half lambda. So this derivative actually reaches the maximum value. The derivative function, derivative of the activation function, reaches the maximum value of 0.5 lambda when net is equal to 0, at net is equal to 0. So if you want to look at it graphically, this is how it would look like for different values of lambda. So 0.5 lambda. So here, if you, this is the graph of the f dash net for bipolar sigmoid. So at net is equal to 0, these are the net values on the x-axis. The negative values, positive values. At 0, it is the maximum. Okay. So if you just look at different values of lambda, this will keep on changing. Okay, and this is the term which you're using in the update of the error signals delta 0 or delta y, delta O and delta y, the output and the hidden layer error signals, right? If you remember delta OK, delta yj. Okay. So this is certainly going to affect, if you're using lambda also as a parameter of this function f of net, then f dash net term will also have that lambda, which will actually go, which is actually going to affect this. So for a fixed learning constant, for a fixed eta or fixed c learning constant, all adjustments of weights are in proportion to the steepness coefficient lambda. So this lambda, the steepness coefficient, that is lambda, uh, it is directly proportional if you keep the learning constant, learning as the constant as fixed. Okay, So generally what is the guideline is you keep lambda as fixed. Don't use different values of lambda. Rather than that, we use the standard value of 1 for lambda, and then whatever learning speed, if you want to control, you go for changing the learning constant one. So that is why we say whenever we want to control the speed of learning, we keep on changing the learning constant. Rather than controlling both learning constant as well as the steepness factor, use control only the learning constant. So whatever functions we'll have, we will just keep lambda to 1. So that is why you will not see lambda anywhere. You will see 1 upon 1 plus e raised to minus net. That's it. Lambda net minus lambda net hai actually. But you're removing that. We're not looking at different steep values of different steepness variants of the function. Okay. So this is for the unipolar signal. So this is about steepness of activation function. We don't tamper with it. We keep it as 1, and we only vary the learning rate to control the speed of training. Next is the learning constant. So the learning constant, basically, we have just discussed that it is going to control the speed of training. So if you want to choose some optimal value for it, there is no optimal value for it. There is no such optimal value of eta. Okay, so it depends on the problem being solved. So you have to do a certain trial and error and see for that problem which is working best. And there is no single constant value which is suitable for different training cases and all that. So you have to actually experiment with this eta values in order to get the best network at the end of the training. So you need to experiment during your entire whenever you're training your network, you need to experiment with this parameter, choose different values and see. So when you have a large value, when you choose a large value of eta, and you have broad minima, which will yield small gradient values when the derivative is smaller, then the convergence will be fast. Okay. On the other hand, where the minima is very steep and narrow, then in that case, you need to choose a small value of eta. Okay, but this cannot be decided beforehand. You need to make certain observations from your data. So how your error gradients and your errors look like. How is your error function looking like? And it is very difficult. It is multidimensional. Okay, so you need to actually experiment with different values of eta. Okay, so if you're going for very large value, it is not advisable because your error landscape might be such that it is steep and narrow. So a large value of eta that is closer to 1, eta value is it's greater than 0 and less than equal to 1, right? Eta is greater than 0, less than equal to 1. Don't choose eta as 1 or very close to 1. Choose it very close to 0, 0.0001 or 0.01. Why? Because there's a case that you might overshoot the actual solution, because what you're trying to do in case of gradient descent is you're moving downhill. So if you're taking steps, so eta is actually controlling the step, right? So step size basically. So if you're going in smaller steps, you might reach the correct minima, but if you take a larger step, you might reach somewhere here, which is not the minima. Somewhat like this. So it is suggested that you go for a small learning constant. So when you're going for eta, whenever you're choosing a value for eta, you of course you have to experiment with different values, but you choose a smaller value. Okay, but if you're choosing a very, very small value, then there is a trade-off again. What is a trade-off? The number of learning steps or the letters might increase in order that you reach the minima. So then what is the solution for this? What is the solution for this? The solution for this is there are some mechanisms which have been proposed where you have what is known as variable eta. Rather than a fixed eta, you have variable eta which is varied throughout the algorithm. So throughout the process of running this algorithm, you keep on varying eta. At the beginning of the algorithm, you take larger steps and then you keep on reducing the step size. You become cautious. As you're going downhill, you become cautious. As your error is reducing further, you become cautious. One such example is Adam optimizer, variable eta. Okay, so modern day networks make use of such optimizers where this learning constant is variable. So variable learning constant is used nowadays because if you're going for a fixed value, and fixed value you cannot choose a large value. That is the trade-off. You cannot choose a large value, and if you choose a small value, very small value, it might take longer to convert. So go for variable eta. So that is the guideline. So basically what we're doing is, as we're going through the learning factors, we are also looking at what are the guidelines that we need to follow while we are going for training in a real world scenario. Next is the momentum method. Now this momentum method is basically used to accelerate the convergence. So sometimes what happens, you are running it, but the algorithm is taking time to converge. So what we do is we introduce one term in the weight update equation, and that is called as a momentum term. Okay, so this is the usual weight update equation that we have, this much. So delta W is minus eta times. Of course, then that minus becomes plus when we compute this function del of E. Okay, and this is the equation that we have seen in the usual training. So what we do in the case of momentum method, we add this term to the weight update, this term, alpha times delta W t minus 1. This second term is called as a momentum term. What we do is, in this, we actually add the most recent weight adjustment. So for weight adjustment at time instant t, we are making use of the previous weight adjustment. Okay, and we are multiplying it by a positive constant, and we are adding it to the weight term, the current weight adjustment. So what happens is, we are using the previous weight adjustment value that we have with us here. So it gets added to the current weight adjustment. So what happens is, you are moving faster. You're moving faster. But how fast? It is not that the entire weight you are adding. You are adding a fraction of that weight. You are adding a fraction of the previous weight adjustment to the current weight adjustment. This is the current weight adjustment, this part. This is the current weight adjustment, right? This is the current weight adjustment. Okay. And this is the previous weight adjustment. You are adding a fraction, alpha times, alpha is a fraction, alpha times the weight adjustment. So you're adding a fraction of the most recent weight adjustment to the current weight adjustment, so that you are actually just boosting the convergence. You are just making it a little bit faster. Okay. So typically, the typical values that is used in practice is between 0.1 and 0.8. That is for the momentum term. Okay. So you will see this as a parameter, and some optimizers use this directly, the momentum term. You see this as a parameter if you look at the library. Okay, the momentum term. Just look at your scikit-learn library, MLP, classify. You will and find out where this momentum term is used. So you can see. So when you're varying, actually, if you're doing experiment 7. So you can vary this also. You can see whether with momentum you're getting better results. Okay, faster results, whether experiment can be done. Next is the network architecture and the data representation. So network architecture is very important. You need to choose the number of input neurons, the number of output neurons, number of hidden neurons. That is nothing but the network architecture. So when we talk about the number of input neurons, the number of input nodes is simply the dimension. How do you determine it? By looking at the dimension of the input vector. Okay. What are the features? There are 10 different features. Simple way of determining the number of input nodes is having 10 inputs there. Okay. Usually this is the case. So usually the input vector is the number of distinct features which are there in the input patterns. So n-dimensional input pattern. So n-dimensional input vector. N-dimensional input pattern equal to n-dimensional input vector. So many input neurons, n input neurons you will have, right? Now, if you're going for some other kind of a pattern, like an image, which we have seen one problem on this. Okay. Sometimes the size, there's one more way of doing this. The size of the input vector is sometimes made equal to the number of pixels in the evaluated image. The size of the input vector is equal to the total number of pixels in the evaluated image. Okay. So that is fair enough. So 3 by 3 image. So how many input? What will be the input vector? It will be 9. Okay. This is the usual case again. This is similar to the previous one. Like this is for a normal pattern where you're characterizing it by features. Okay. And this is a planar image that you're considering where you're characterizing it by pixels. So number of pixels equal to the size of the input vector. Okay. But this same thing can be done in another approach, and that is by using a vector size of 2 only. Now, how do we do this? Let us, okay. So actually there's a trade-off which exists between the number of training patterns P, which are needed to create the training set, and the dimensions I of the input vector. The number of training patterns that you have in the training set is P patterns. There are P patterns in the training set, and the dimensionality of the pattern is I. There is a trade-off which exists between this. Okay, so let us see in this example. So there are, let's say there are these planar images that we have with us in a 3x3 grid. So CIT, so C and I are shown here. So if you're using the first approach, the typical approach, then if we just use each pixel, 9 pixels to characterize each image, then you just have to establish a representation for those pixels. Okay, so it's like 1 1 1 wherever that pattern is there. So that is a 1, rest all is 0, and then 1 1 1. So, and we are stacking it row wise here. It could be column wise. Another way it could be column wise. We're stacking it row wise. So 1 1 1 1 0 0, right? 1 1 1 1 0 0 1 1 1. This is C. Similarly, you can see this 0 1 0 0 1 0 0 1 0. That is I, right? T is not shown here, but that is how you will do it for T in a similar way. This is the first approach. Now the second approach, let us look at the second approach where we're using 2 neurons. So for the second approach, what we're doing is we are actually looking at this is the second approach. There are 2 neurons, 1 1. So we are looking at the row number. This is the row. These are the rows. These are the columns. We're looking at the row number and the column number. So for each pixel, we are looking at row number and column number. So how do you represent it? The first pixel first will be represented by 1 1. Second will be represented by 1 2, and so on. Okay. So in this case, what will happen? This will change. See, in the first case, N is 9 and P is 3. That means there are three patterns that you have C, I and T, but N is equal to 9. What is N? N is the dimensionality of the input vector. Okay. Now in the second approach, what we are doing is we are reversing it. So we are making it 2. So we are representing each pixel by the row number and the column number. So N becomes 2. The dimensionality of the input vector becomes 2. But now that you have 9 input vectors now. You have 9 input vectors. Okay. So 1 1, 1 2, 1 3, and so on. So now 1 1 will correspond to class C and T. 1 2 will correspond to class C, I and T, something like that. Okay. So this is a somewhat complicated representation. Okay, but this is also one way. You can think in a number of ways for doing the same thing. Okay. So if you're going for this, now you have seen everything has changed. The dynamics have changed. Okay. So this is important, how you are choosing to represent your input. How you are choosing to represent your input will actually change everything. It will change the architecture of your network. So the usual way, the traditional way will be very simple. We follow it row wise or column wise stack, and then consider patterns equal to patterns. You don't complicate it. But this is a somewhat complicated representation that we have here. Okay. So that is about number of input neurons. Next is choosing the number of output neurons. How do you choose the output neurons? Again, you have k classes, so you have k number of outputs, right? So if you have k classes, k outputs, and you're done. So each output neuron corresponds to a single class. So one will at a time, only one will be active. That is one way. The other way is you just reduce the number of output neurons. How do you reduce? You are using some kind of encoding. Okay. So 0 0, you use class 1 is 0 0, class 2 is 0 1, 1 0, 1 1. Okay. But if encoding is done, decoding also has to be done. If you are using this kind of an encoding, the appropriate decoding also has to be done while you are actually predicting the output. Okay. So again, there's a trade-off. So it is up to you. You go for a simpler way or you go for a complicated way. Both are going to give you results, but the time in which the network will train, everything will change because the network architecture has changed, right? What was earlier like k was they say 4, now it has become 2. There were 4 classes, so there were 4 output neurons. Number of weights will increase, right? But now you have reduced the number of weights, you have reduced it to only 2 neurons. Number of weights will decrease, right? So training time, everything will be affected. Next is the number of hidden neurons. How do you decide the number of hidden neurons? The number of hidden neurons is very, very important because that is actually what is going to enable you to solve the problem. Because, okay, input and output representation is fine. Okay, I choose one thing and I go ahead with it. Ultimately, it's going to train. But number of hidden neurons is the most important thing because that is going to decide how you're classifying. So, you are making lines everywhere, how you're going to classify the patterns, right? How many such lines are required and all that. But the thing is, there is no standard. There is no standard specified for choosing the size of the hidden layer. So if you're considering a single hidden layer, you cannot predetermine what should be the size. There is one formula which you can use, which can be used as a guideline to find out how many hidden layer neurons are needed. That is, this tau is equal to log of m to the base 2. Now this means if there are m classes, so for example, if there are 4 classes, then I need to start with at least 2 neurons, log of 4 to the base 2. So I need to start with 2 neurons. So I will require 2 neurons minimum, but I have to start taking values from 2 up till the dimensionality. So suppose the dimensionality of the input is 6. Okay, so I start with 2, and if 2 is not giving me good results, I just change my 2 to 3, go from 2 to 3, and check whether 3 is giving me better results. If it's converging, it's giving me good enough results, I will not go for 4 neurons. I will not complicate it. I will not increase, because see, if I increase the number of neurons, I might have more number of weight connections, and it might unnecessarily make my network complicated. So whenever I'm choosing the number of neurons, I start with this magic figure. This is one magic figure that I have. Tau is equal to log of m to the base 2, where m is equal to the number of classes. Okay, but this is the minimum value. I can keep on increasing it till n, but I be careful. I don't directly say tau is equal. So if suppose 2 is this is 2, and then n is like 10, just an example, I don't say it is like from 2 I directly go to 8. Maybe I go to 4. Next time I try with 4 hidden neurons rather than 8. Okay, so gradually I increase the neurons in my hidden layer gradually, not very and the jumps that I will have will not be very large jumps. There'll be shorter jumps as I'm going from 2 towards 10. Are you getting it? So that is a guideline that needs to be followed. Although there's no formula which will directly give you, okay, this is the number of inputs, this is the output, okay, these are the hidden neurons I need to have. No. Okay, you can follow this guideline while you are experimenting with what is the necessary number of hidden neurons to solve the problem. And finally, the training time. So how do you make your training time? What decides the training time actually? So whenever you're going to train your network, it is important that you, instead of having only a training set, you actually divide it into two parts. Okay, one part your is your training patterns, and the second part is your training testing patterns. During training, whatever number of patterns you have, so first of all, total in your data set you divide into two: training and test set. Okay, now from this test set is something which is not going to be used at all in training, so let's forget about this, that 80-20 split or 70-30 split. So remove that, just let us not look at this. But from this training set, there are two disjoint sets that you need to create. It is suggested that you create two disjoint sets. One is the training set, okay, and second is, they are calling it the training testing patterns. Training testing, train test. Okay, now what do you need to do is the weight adjustments which are based on the training patterns. Weight adjustments that you do will be based on the training patterns. However, at regular intervals during the training at regular intervals, what you need to do is you need to compute an error using the training testing patterns, the second set you have. So there are two sets. One is the training set, the usual training set. Okay, so for example, your data set is comprising of 100 patterns. Just a very simple example. Out of that, 80 is your training set, 20 is your test set. Test set you have to forget for now. Just forget it for now. So 80 is your training set. From this 80, you choose a large number of patterns again here, which you're going
Hello,
to.
ma'am.
Yes,
Ma'am, it's 122. We have major project also at 2.
I'm just about to finish it, Shagun. Give me 2 minutes.
Okay, ma'am.
This is the last slide. Okay. Yeah. So this is 60. So from this, you just take out a large set, which is 60, and the second is 20. Okay. So what you do is, again, you divide this training set into two. Again, a larger chunk which is used for training, and a smaller chunk which is used for evaluating the error. Okay, so compute the error using the training testing pattern. Okay, so as long as the error decreases, you continue the training. So if the error keeps on decreasing, so what you're doing, you are training on one set, this particular set. Okay, computing the weight, doing the weight adjustment using this set of patterns. But for computing error after regular intervals, after say 10 epochs, you are testing for this, looking at this and finding out the errors. If the error keeps on decreasing, you keep on training. On the other hand, if at that point when the error begins to increase, you stop the training. Okay, because when it begins to increase, it means that the network is actually memorizing the training patterns. It's memorizing these patterns, the 60 patterns. These are unseen by it. These 20 are unseen by it, but we are using it during training. It's not the test set. Remember, this 20 is not the test set. This set is called the validation set. Right? Validation set, everyone knows. Okay. So with the help of the validation set, you can actually make the network generalize, so that it does not memorize the patterns. So that it does not memorize the patterns. This is a strategy using the validation set, so that it does not memorize, and it improves its generalization capability. Okay, and at that point you stop the training. The moment the error increases, you stop the training. Okay, so that is the last factor, and I'll stop now.
Hello, ma'am.
Yes.